In this unit, we're going to learn how to find antiderivatives of functions of multiple variables. Look at this illustration here. Sorry, I didn't mean to move it. You can see with positive x here, positive y here, and positive z going straight up, if we have an area on the xy plane that's in this case bounded by a particular x value on either edge, and then two functions where y equals some function of x, we have this area bounded, and then that area is capped by this surface where z equals that function of x and y. If we take a small column that's based on the xy plane and we extend it up, you can see that the whole volume underneath here that's bounded by this area on the xy plane and this surface, we can find the whole area of the whole volume by taking the area of that column times its height and then adding an infinite number of those together. This is just like when you learn to find the area between two curves, except now it's in 3 dimensions. So the area of each of these columns is going to be dx on one side and dx on the other, where the x in this case is bounded by constants and y is bounded by functions, and then the height of each of those columns is the function f of xy. So you see how this integral is set up. Notice that we're doing dy and then dx. You're going to take that interior piece first. Let me highlight this for you. You're going to do this integral first. And you see from the illustration that the y value is going to go from one function to another. From g of x, which is closer to 0, right? So this is the lower one, and h of x is the higher one. So we're going to integrate our function with respect to just y, and then we're going to evaluate from one function to another. Then once we get this answer, we'll be left with an integral with constant limits, and we're going to integrate with respect to x by itself. Sometimes the surface that lies on the xy plane that is capped by this z equals f of xy, sometimes it's just a rectangle, so that the limits on x are constants as well as the limits on y being constant. So if we can integrate with respect to x from the limits of the x value, evaluate that with respect to just x, then take the integral with respect to y and evaluate that between the two constants. If everything is constant, we can switch this order. It doesn't matter which one goes first. We can do y first and evaluate at the y limits, and then do the x and evaluate at the x. Let's look at an example of this here. We're going to do this both ways and show that we get the same answer. In the first part, we're going to integrate with respect to x first. Let me highlight this here. We're going to integrate with respect to x, evaluate it using x equals those limits, and then move on to integrate what was left with respect to y and evaluate that there. So here we go. We're going to integrate with respect to x first. So this outer integral stays. All right, integrating x with respect to x gives me x squared over 2. Integrating 5y with respect to x, I get plus 5xy. We're going to evaluate that with x going from 1 to 3. And the dy integral is still there. So now I have the integral from 0 to 2. I've got plugging in the 3 for the x, I get 9 halves plus 15y minus, plugging in the lower limit, the 1, I get 1/2 plus 5y. We still have the dy integration to do. So let's simplify always and forever, amen, before we integrate. I have 9/2 minus 1/2 gives me 8/2, so that's just a 4. And I have 15y minus 5y, which gives me positive 10y. This is still being integrated with respect to y. So integrating, I get 4y plus 10y squared over 2 gives me 5y squared, evaluated from 0 to 2. So I plug in the 2, and I get 8 plus 5 times 2 squared. 5 times 4 is 20. Then I'm going to say minus, plugging in the 0 gives me nothing, and my answer is 28. All right, doing it the other way, let's start by doing the interior integral, that's just with respect to y, evaluated from 0 to 2. So we still have the outside integral. We're going to integrate x with respect to y. That gives me xy plus 5y squared over 2. We have to evaluate that from 0 to 2 and then do the integral with respect to x. So I have from 1 to 3, plugging the 2 in for the y gives me 2x plus 5 times 2 squared divided by 2 gives me 10. Now that we've evaluated it and it's simplified, we can do the outside integral with respect to x. So integral of 2x is x squared over 2, and the 2's cancel, plus 10x evaluated from 1 to 3. Plug in the 3, we get 9 plus 30, minus, plugging in the 1, we get 1 plus 10. So this is 39 minus 11 equals 28. So you see that if we have just a rectangle, all of our limits are constants, it doesn't matter the order that we integrate in. However, if your boundaries have functions in them, you need to do that integral first and evaluate it at those functions, and then leave the constants for the outside integral. In this example, we have this surface f of xy is x plus y. We've got y is bound by function, whereas x has constant boundaries. So the x integral has to be outside, while the y integral is inside. So we're integrating f of xy with respect to y first. So let me highlight that in blue. And we have to evaluate it at those functions. So integrating, we got xy plus y squared over 2. We're going to evaluate that from the lower limit, 0, to the upper limit, 1 minus x. So plugging in the 1 minus x for my y gives me x times 1 minus x. We're going to square it here to over 2. And that still has to be integrated with respect to x. Do not integrate this. You need to simplify it first. It's going to make a huge difference. So distributing the x, I get x minus x squared. Foiling this out and then dividing it by 2, term by term, is going to give me a 1/2. 2x divided by 2 gives me an x, and then I have x squared divided by 2, and it's positive. Notice that I have x minus x, that cancels. I have negative x squared, a whole one, plus a half one. That's going to give me minus x squared over 2. So I'm integrating still from 0 to 1 with respect to x, and my function is negative x squared over 2 plus 1/2. Integrate that with respect to x now. I'm going to get x cubed negative over, dividing that by 3 gives me a 6, and then 1/2 times x. Plugging in the ones, I get minus 1/6 plus 1/2, minus plugging in the 0 gives me 0. Need a common denominator, which is going to give me minus 1 plus 3, or 2 over 6, which is 1/3.